So just to recap from the previous video, we brought in a bunch of terminology to be able to talk about probability and random experiments. So a random experiment is something that's repeatable, an activity which is repeatable, where we know what the possible outcomes are, but we don't know exactly which outcome is going to happen until we've actually done the experiment. We give the set of all possible outcomes a particular name, usually called the sample space. In terms of set theory, this is our universal set. But when it comes to probability, we usually use an S instead of a U, but either one is fine. Now, our sample space is the set of all possible outcomes, but sometimes we want to talk about a subset of those possible outcomes, in which case we use the term an event. It's a collection of possible outcomes, so it's a subset of our sample space. And the frequency of an event A, which we denote using the cardinality, is the number of successful trials if we do n trials overall. So a trial is running the experiment once. We can also talk about the relative frequency of an event, and this is just where we divide the frequency by the total number of trials, and this gives us the proportion of successes to trials, where a success means that event A happened. So let's just look at an example. So we've seen this before, rolling two fair six-sided dice and measuring their sum, and we've already seen that the set of all possible outcomes, our sample space, is 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So just to make the difference between an outcome and an event clear, an outcome is an element of S. So an outcome could, for example, be 4, or it could be 12, any one of those. An outcome is just one of the possible elements of the sample space. But an event doesn't have to be just a single outcome, although it could be. So for example, an event might be getting an even number for the sum, in which case this set would be the subset of S of all even numbers. So that would be 2, 4, 6, 8, 10, and 12. Another example, though, would be the set B, which is equal to simply getting a 6. So here we're thinking of 6 as a subset, whereas when we're talking about an outcome, we're thinking about an element. So that just gives us some clarity between event and outcome. So we can use the notions of relative frequency that we built up in the previous video, together with our knowledge of sets, to formalize our ideas about how to measure the outcomes of the experiment and what we expect those measurements to give us. So let's just note the following things that we actually saw in the previous video. Firstly, relative frequency. So remember, this is the size of the outcome set, or the number of times in which we have a success for that particular event divided by the total number of trials. So relative frequency. Well, it can't be negative since we're counting things. So cardinality can't be negative. So our relative frequency can't be negative. And if we have two disjoint events, so two events which cannot occur simultaneously, and those are the only two things that can happen, then we should get a sum of 1, because either one of them happens or the other. And similarly, if we have a collection of disjoint events, then if we add up the relative frequencies, then the relative frequency for that collection should just be the sum of the individual relative frequencies. So what does that mean? Well, now we can start talking about probability. So we're going to talk about the probability of some event A, so some subset of the sample space happening. And we translate what we've just talked about into the following. We say that the probability of some event A happening has to be greater than or equal to 0. So remember, we said that our probability is going to be a number between 0 and 1. 0 means it never happens, 1 means it always happens. And we're starting to build up how this works. So our probability of something happening has to be bigger than 0. The next thing that we note is that the probability of something happening, so that we're saying our sample space includes everything that could possibly happen, and the probability of something within there happening is 1. And then when we were thinking about disjoint sets, well, if our two events are disjoint, so their intersection is 0, then the probability of both of them happening is just the sum of the probability of each of them happening. And you can extend that to having a whole lot of sets that are pairwise just disjoint, and then the probability of the sum of those happening is just the sum of their probabilities. So this looks like a bunch of complicated maths, but really it's just formalizing into maths the ideas that we had in the previous slide. We can think about some more things that follow on from this. So for example, if we have, so here we're just so that we've got a picture of this, we've got our sample set and we've got some event A, which is a subset. Well, if we take the probability of A and add to it the probability of not A or A complement, then that must also give us 1. And this is because we know that A union A complement is equal to S, and we know that our probability of S is equal to 1. So by the previous slide, we must have that if we sum the probability of an event and its complement, that gives us the same as the probability of the whole sample space. Our next idea is that if we're thinking about the probability of nothing happening, that must be 0. So nothing is the empty set, and since we do the experiment, something has to happen, so our probability of nothing happening is 0. Now if we imagine what's happening, we've got events A and B, so let's just draw a little sketch over here. So we've got an event A, and notice A is going to be contained in B, so here's my B. Then the probability of A happening must be less than or equal to the probability of B happening. And this kind of makes sense. B has got more possible outcomes, so it's more likely to happen. Our next theorem says that the probability of A has to be less than or equal to 1, and this is just because we know that the probability of our whole sample space is 1, and we must have that A is contained in or potentially equal to our sample set. And then finally, if we're thinking about the probability of two events, the union of two events happening, we've seen what happens when they're disjoint, but when the events are not disjoint, we have a rule that looks very much like our inclusion-exclusion rule. So what we're saying is that if we have events A and B, which are not disjoint, we take the probability of A happening, we add it to the probability of B happening, and then we have to subtract off the probability of their intersection, because otherwise we'd be double counting. So it's the same idea as we had for inclusion-exclusion. And just one more bit of terminology. A special case that arises is when all outcomes are equally likely. So we saw this when we were thinking about a fair coin and tossing it, it was equally likely that it would give heads or tails. Or if you roll a fair six-sided die, then you're equally likely to get 1 or 2 or 3 or 4 or 5 or 6. So just to put that in formal language, the probability of equally likely events, well, if the outcomes in our sample space are equally likely, then for some event in S, the probability of that event is just the size of A divided by the size of S. And you can think about why that works for a little bit, but it's actually quite straightforward. So let's look at some examples. We're going to suppose that each child born is equally likely to be a boy or a girl. Now, this isn't actually scientifically true. The numbers are slightly different, and of course there's the whole issue of deciding exactly what a boy or a girl is. But let's just take the simplistic point of view. We're going to assume each child boy is either a boy or a girl, and it's equally likely to be a boy or a girl. And in a particular family, we're going to suppose that there are 2 children in the family. So we're going to think about the sample space of possible children or pairs of children that the family could have. So we're also not considering the case of having twins or anything like that. So just to be clear, we're going to denote a girl born first and a boy born second by girl boy, and so on. So take a moment to list the elements of the sample space whose outcomes are the possible genders of the 2 children in order. So if we think about this, our sample space, well, we can have a girl born first, followed by a boy, a girl born first, followed by another girl, boy first, girl second, or 2 boys. So in our very simplistic setup, those are the possible outcomes of having 2 children. So now we want to think about elements of each of the following events. So events, remember, are subsets of our sample space, and we want to find the event's probability. So our event that exactly 1 child is a girl. Well, let's call this event A, and this consists of all the outcomes where we have 1 girl. So in our first outcome there, girl boy, girl girl has 2 girls, and we want exactly 1, so that's not going to be in our sample space, and boy girl. So we have 2 possible outcomes in this event. And this is where we use our equally likely situation, which we saw up here. If the outcomes in S are equally likely, then for some event contained in S, the probability of that event is just the size of A over the size of S. Well, we've said that the probability of having a boy or a girl is equally likely, and we're going to also assume that the probability of the second child is equally likely. So in this case, since our outcomes in S are equally likely, we have that the probability of our event getting exactly 1 girl child is the size of A over the size of S, and this is just going to give us 2 over 4, which is a half. Okay, now we want to think about the event that both children are girls. Well, there's only one event. There's only one outcome in that event, which is girl, girl. And so we have the probability that both children are girls is going to be 1 over 4. And we could think about the event that no child is a girl as an event C, in which case we're looking at boy, boy. And again, we get that the probability that no child is a girl, i.e. both children are boys, must also be 1 over 4. So you can see how we're using everything we developed with set theory to help us figure stuff out with probability. So here's another fairly classic example. We're going to consider a box with 3 balls, 1 red, 1 white, 1 blue. And we want to know the sample space of randomly pulling out 1 ball. Well, our sample space, I'm just going to use R, W, and blue, and B. Our sample space is red, white, or blue. What is the probability of randomly selecting a red ball? Well, notice that whether you select red, white, or blue, assuming you don't kind of check to see first, these are all equally likely. So our probability of selecting a red ball is 1/3. And remember, and I've turned selecting red into an event whose probability I can measure. Technically, it wouldn't be wrong to write this, but we think about the probability of events, not outcomes. So we turn outcomes into events by thinking of them as a set. Okay, so far so good. But now suppose that we're looking at the same thing. So we've got a bag with red, white, and blue ball, and we're going to do 2 trials. In the first trial, we're going to happen to select a white ball, and we're going to throw it away. And the second trial, we want to think about the probability of randomly selecting a red ball. Well, the thing is that we know by the time we get to the second trial that our sample space, so I'm going to put an S2 for the sample space of our second trial, really only consists of pulling out a red or pulling out a blue, and therefore our probability of selecting our red is now 1/2, which is different from the probability that we had initially, which was just pulling out a random red ball. What's changed is that something happened in a previous trial which affected the probability of the second trial. And when we have a situation like this, we call this conditional probability. So here, the outcome of our second trial is conditional or depends on what happened in the first trial. So here we have to use past history to calculate probabilities. We didn't have to do that in some of the previous examples, but now we do. How can we formalize this? Well, we say the probability of event B given that A happened. So let's just write that. This is the probability of event B given that A happened. And it turns out is given by the probability of A intersection B divided by the probability of A. And if you draw a Venn diagram, this can help a little bit. So we've got a probability space here. Here's our sample space. And we've got an A and we've got a B. Now suppose we know that A happened. Well, then we know that we're definitely living in this space. So now, if we want in the next trial to think about the probability of B happening, what we're really looking at is we want the probability of A intersection B. But we need to take into account that in fact, for our second trial, really it's kind of like we've reduced our sample space to A. And that's why we've got over here our probability of B happening, given that we know that we're actually in A rather than the whole of S, is given by the probability of A intersection B divided by the probability of A. So let's go back to our previous example and see if we can use the rule we just came up with to solve it. So I'm going to slightly reword this question. What we were originally given was suppose that for the first trial we select white ball, which we throw away. So I'm going to rethink of this experiment as an experiment that has 2 bits. The first bit is you select a ball and you remove it. And then the second bit is you select another ball. In which case, we're thinking about the particular case in which we first select a white ball and then select a red ball. We'd like to know the probability of that whole event. Well, let's start out by considering the sample space of this experiment. Well, our sample space consists of all the pairs of possible balls. So we could draw white first and then get blue. We could draw white first and then get red. We could draw red first and then get white, red first and then get blue, blue first, white, blue first, red. So if we do this experiment, these are the 6 possible things that could happen. Now let's look at what actually happened. Well, we know that we selected a white ball first. So we know that the event that actually occurred was either of these two. We're either going to end up with white-blue or white-red because we know that we got a white ball first. The next thing we want to think about is the probability of randomly selecting a red ball second. So we're going to think about our second event as the probability of randomly selecting a red ball. Well, looking at our sample space, the places where we got a second ball that was red was either white-red or blue-red. So that event looks like white-red, blue-red. And what we actually want is the probability of this B, the set B, the probability of getting and what we actually want is the probability of B, which is getting a red ball second, given that we know that we got a white ball first. So we know that event A happened. Well, our previous rule says this needs to be the probability of A intersection B divided by the probability of A. If we look at A intersection B, we see that the only thing that they have in common is white-red. So this is going to be the probability of white-red divided by, and this is going to be the probability of A. So if we can figure out these two probabilities, then we're done. Well, if we go back to our original sample space, we know that these outcomes are all equally likely. So each of these will have a probability of 1/6. And since they're also disjoint, if we look at the probability of A, it's going to be the sum of the probabilities of each of the outcomes that makes up A. So if we put this all together, we must have the probability of white-red is 1/6, and the probability of A is 1/3, and finally, if you work this out, you'll find that this gives a probability of 1/2, which is what we figured out before, but now we've done it using our formal probability. So it might take you a little while to get the hang of this, and that's why practicing is important. Notice that the key things that helped us here were writing down the sample space and the events that we were interested in correctly, and then knowing the probability of each of the events, of each of the outcomes in our sample space. So you should start every problem that you can by writing down the sample space and the events that you're interested in, because this will really help. And in order to practice that, here is an example for you that you should work on. So this is just another urn containing balls and thinking about possibilities. Work through these and see how you do. Just a quick note, we can in fact use the rule we just came up with, slightly reordered, to figure out the probability of A intersection B if we know the probability of B conditional on A and the probability of A. It's just reordering. Remember, we had probability of B conditional on A was probability of A intersection B over probability of A. We're assuming that the probability of A is not 0, multiply both sides by P of A, and there you go. So do spend some time working through this problem, and I will put the solutions up in the final notes.